So V is pointing out in the radial direction. E is pointing out in the radial direction. V is equal to the Q over 4 pi epsilon 0 r. It means that if you look at a part, a spherical part, for example, this part, that has the charge at the center. And if the charge at the center, it means that on every point on the surface, the distance to the center are equal, like on every point on the surface. So if you look at this point, it's r. If you look at this point, it's also r. If you look at this point, it's also r. It means that this surface is a equipotential surface, but it is just a sphere. Okay, this sphere is an equipotential surface. And if the surface is a sphere, if you look at this point, you know that the electric field point in the radial direction. What is the angle between the electric field and the surface area at this point? What is the angle? Because this is a sphere, like an electric field point in the radial direction. What is the angle between the electric field and the surface here? It's normal, right? If you have a sphere and you look at the radial direction, on every point on the surface, the radial vector is normal to the surface, right? So you can see that the equipotential energy in this case is normal to the electric field. But we can prove in general that the equipotential surface will always normal to the electric field. This is maybe the most simple example. The electric field and potential from a point charge. Okay. And that is really, I will talk about that expression soon. That is very important. Okay. Because we know that in an isolated conductor, if we have an isolated conductor like in this figure, we discussed before that the electric field inside is zero. And if the electric field inside is zero, it means that the electric potential is a constant everywhere inside the conductor and also on the surface too. Okay? So we can write this as a V is a constant. V is a constant inside the conductor and also on the surface too. And if V is a constant on the surface, it means that on the surface of the isolated conductor is an equipotential surface, right? Because the potential is constant on the surface, and that is the definition of the equipotential surface. And since the surface of the conductor is an equipotential surface, it means that the electric field will be normal to the surface, right? Will be normal to the surface. Again, we can use this I mean, we can use the isolated conductor as an electric shield, and also we can use it to I just forget it, the word. We can use this concept to create the device that protect like the building from the lightning. What is it? What is it? Anyone? Yes, it's in Thai, but in English I just because like in the like the high building, like this in the building, not. In fact, it is the standard now that if you build the building, you will have to put this thing. And for example, if you have the building and you put maybe a copper stick or the copper rod on the top of the building, and you also have the wire and put it to the ground. Okay, we may think that this copper is like a isolated conductor, and in the thunderstorm, when you see the lightning, it is because we have the electric field around that region, and if the electric field is intense enough, you can have the electric charge move. Sometimes it's moved from the cloud to the ground, to the to the ground. Sometimes it's moved up from the ground. But in any case, it means that you have approximately the electric field something like this. But once you put an isolated conductor here, and we know that on the surface of the isolated conductor is an equipotential surface, and the electric field will perpendicular to the surface of the isolated conductor. It means that the electric field will bend to the surface of the conductor, the isolated conductor, something like this. So it means that if you have the lightning is nothing but the current, the charge move maybe from the cloud to the surface. So if you have that happen, like if you have the charge move, instead of move to the ground, it moves to this conductor. Okay, and then you can connect it to the ground, and you have the charge move to the point you want it to go, and it will not move to the roof of any house. You can prevent the damage from the lightning, and this comes directly from the fact that when you place an isolated conductor in the region with electric field, the electric field will bend to the conductor. The reason that we have this bending because it has to be normal to the surface of the conductor, so it will bend to make it normal at the surface, something like this. Okay? So we can prevent the damage because it's just like it pull, the conductor pull the electric field to itself. Okay, so that is the principle of this device. Okay, and the last thing for this chapter, the